All right. Hi, everyone. As my wonderful presenters and introductors just said, I am Elizabeth Sebastian. And as they mentioned, this unit plan passed SMD Product review, which was no easy feat. It took about a year's worth of work to do. But if you have the opportunity to do it, I highly recommend it. So this particular unit plan is called the Heat is On, Urban Heat Islands, Detection Strategies and Mitigation Solutions. And I'll go into what that term means if you're not too familiar with it, and also what we do to mitigate these urban heat islands, as they all are part of my unit plan I developed. So let's get to it. So I first wanted to introduce myself a little bit more. I went to Towson University, where I earned a bachelor's in education. And during my senior year there, I presented at the Maryland Math Teachers Conference on how to incorporate art into mathematics. So in terms of STEM, that would be called STEAM, and that's what we've kind of been focusing a lot towards lately. And I also attended the National Institute of Aerospace's STEM Institute, which was a week-long program where I learned how to incorporate STEM into the classroom. After that, I taught a year in Baltimore County, but then moved up to New York, where I've been teaching at Fusion Academy ever since. I am the head of the science department there and also the technology liaison. And back in 2016, I was awarded Teacher of the Year for my campus. As Matt mentioned, the past 3 years, I was part of a program called the Climate Change Research Initiative, or CCRI, where I spent the year conducting research on the urban heat island effect, but at the same time developing this unit plan. So I did that for 3 years, and during my first year, I published an article with my research team in the Urban Climate Journal in 2018. I also work at Infiniscope as well, where I serve on the Education Advisory Board, where I review and create interactive science lessons online. So I recommend checking that site out as well, as it's a NASA-funded site. And then in the future, I'm working on getting my master's in instructional technology, which I'll be starting up this summer, and then take that and become a doctorate in science education, and then hopefully one day become an education specialist. So Matt already kind of gave you the rundown of the Climate Change Research Initiative, so I'm just going to go ahead and skip over for that for now. But if you want information about it, please reach out to Matthew or I, and we can provide the information. I wanted to introduce my team that I worked with this past year. My two mentors were Dr. Reginald Blake and Dr. Hamadrez Narizi, and I believe I saw Dr. Narizi on the chat there. They work out of New York City College of Technology, or what we call City Tech. And I also worked with a graduate intern named Anna Leibowitz, who is based out of Columbia University, an undergraduate intern, Claudia Yanos, based out of the University of Chicago, and a high school intern, Matthew Billick, who's based out of Brooklyn Tech High School, which is right down the road from my school. So I wanted to first go into the research that I conducted with my team, because it really is the core of the unit plan and how I developed the lessons for the unit plan. And so our campaign was called the Remote Sensing Field Campaign, New York City's Urban Heat Island. And what we wanted to know was, how can satellite and ground-based data be combined to create detailed and accurate map of urban heat on a neighborhood scale? We understand it very well from the citywide scale. We can see those hot and cooler spots, but there's a lot of neighborhoods within New York City, and we wanted to understand at the micro level a little bit more what's going on. So from that, how can such maps best be used to mitigate against and adapt to extreme heat events? We're all about taking action, so we need that information in order to pinpoint what areas we need to focus on and where to take that action to. And then lastly, empowering the citizens. So how can citizen science empower local communities to adapt to and mitigate extreme heat? And this is a big component that I was very proud to work with my mentors about, because you can talk about it in the government offices, you can make different laws, but really what it comes down to is the citizens and understanding where they live and how it's going to affect them and what they can do. So I talk a lot about this term, the urban heat island effect. So I wanted to first go over that term if you're not too familiar with it. In the summertime where it's heightened the most, the urban heat island effect is where we have the thermal energy being trapped within cities because of non-porous surfaces such as asphalt and concrete. And since cities have a lot of asphalt and concrete, that lot of heat gets trapped there. And if you compare it to suburban and rural areas, there's a lot more porous surfaces such as soil and grass, and then we have shrubbery and trees that will actually release that heat back out into the atmosphere, so keeping the energy budget balanced. But in cities, we don't really have that much vegetation, so a lot of that heat gets trapped, creating the urban heat island effect. So what we saw is that the urban heat island is not uniform. We can see on the map to the right that there's cooler spots, like in the middle of Manhattan there's a nice blue area, that's Central Park, but then hotter spots, like if you look at the bottom right, that's JFK Airport, where there's a lot of concrete and asphalt. So we wanted to be able to measure this urban heat island at the neighborhood scale using a variety of tools. One is satellite data, which we'll see in lesson 1 of the unit plan. 2, thermal cameras, which we'll see in lesson 2. Air temperature and humidity sensors to keep track of the air temperature and how much humidity is impacting that temperature. But then also weather station data to use as a reliable source to check in and see what the average is for the area. So how can satellites come into play? So all the previous images you saw in New York City depicting those hot and cool spots come from satellites. And the one for those images in particular is a satellite called Landsat 8. It has a very high resolution and can help us identify those hot spots and cool spots and help us really define where to go with our ground research. So it will in turn help determine which interventions will be effective, such as white roofs, green roofs, and tree planting. So part of the reason why we look at this is because in New York City, in particular where I live, 72% of that 305 square miles is impervious surfaces like asphalt and concrete, like we see in this image here in Midtown. So we want to make sure that the thermal energy is not being absorbed. We want to reflect it back out to keep that energy budget balanced. So it poses the question, how can we reduce the surface absorption of the budget, even if it's just by a few degrees? How can we restore that energy balance? And sorry, the image didn't pop up in this one, but why study this? What it really comes down to is human health. And what we see in the US is that the #1 natural killer is heat waves. And the 95 Chicago heat wave really brought to attention how bad this could be, where we saw almost 750 people killed in 1 week from that heat wave. And there are a lot of populations within cities that are at risk. The children, elderly, people with health conditions, and people living in poverty. And with projections that I'll show you on the next slide, heat waves could be longer, stronger, and more frequent. So that's why we wanted to really focus on this, both capturing what we currently see and then implementing mitigation solutions to reduce those effects. I always like to show this to my students as well, because it just shows what happens based on models, what could be the future. If we take no action now, take no mitigation solutions, don't implement anything, we could see a huge increase of the average amount of days that are above 100 degrees Fahrenheit. So a lot of those dark reds and those like darker oranges, we can see dominate almost half of the United States. So if we take slow or rapid action, that area decreases by a lot. So by putting in those mitigation strategies, we could see a better future when it comes to reducing the amount of days that are above 100 degrees. So our methodology was to go down a stretch of Brooklyn, about 5 blocks in span, and we picked this particular area because it has a hot spot, a cool spot, and a medium spot. And as you can see in the pictures, a lot of it's impervious surfaces, but in that 4th location, the blue marker, that's actually a green street where they had a lot of trees, a lot of bushes, a lot of what we call bioswales in order to help reduce the temperatures there. So we looked at each location, 4 types of surfaces. 2 of them are non-porous, the concrete and asphalt, and 2 of them porous, soil and grass and plants, if they were available. And we used a FLIR thermal camera, and we compared it with satellite data from Landsat, Terra, and Aqua. And this is what we found. So every point on this graph is a data point that we extracted from our research. And so the ones that are in yellow and orange are those unshaded, non-porous surfaces like asphalt and concrete. So overall, they were much higher than the porous surfaces in shaded regions, such as plants and soil. The solid line in the middle is the average temperatures of all the data, and the triangles and squares actually represent the Terra and Aqua data. So the squares are the Terra data, and the triangles are the Aqua data. And what we see is that the data that's being picked up by the satellites is right around the average temperature line, but picking up a little bit on the cooler side. And that could be due to the angle at which the satellites are capturing those images. We also saw that with Landsat. So the orange are the unshaded areas, the blue are the shaded areas, and the green is the Landsat data. And so we saw that the satellites were picking up the cooler areas, but overall picking up the hot and cooler trends that we saw with the satellite data initially. So conclusions, the satellite picks up the overall trends with urban heat island effect, but doesn't pick up quite to the higher temperatures that we see in the unshaded areas, which could be due to a number of factors. And so I know when I last left off, we were talking to people at Landsat to see what we can do to prove even more if that's an anomaly or if that's something we encounter consistently with Landsat data. So all of that leads to how I created this unit plan. So all the strategies I just mentioned that my research team took, I implemented into this lesson plan. So when I go through the lessons, you'll see a lot of that methodology being talked about in each lesson. So my overall goal was to teach students how to use innovative technology to understand the changing climate in urban areas and create solutions to the ongoing environmental problems in cities. So I'm first going to give a brief overview of each lesson, and then I'll go into more detail of what each lesson entails and the resources I've used for it. So the first lesson, the students are going to get right onto that satellite data and learn how to extract satellite data using a website called EOSDIS Worldview. From there, in lesson 2, they're going to go outside and start taking ground measurements, just like my research team did. You collect satellite data, you have to also collect ground data as well. Lesson 3, they're looking at a term called urban heat island intensity, which is looking at urban heat island over a span of years and seeing which spots are consistently higher intensity of the urban heat island effect. Lesson 4, they're learning about a mitigation strategy called bioswales. So they'll learn about the different parts of a bioswale, what the purpose it has, and how it can help with reducing the urban heat island effect. And then lastly, lesson 5 is the Capstone Project, where they'll create an infographic poster based on the data they collect on a specific city, propose mitigation strategies, and how that will help the city. All right, so let's go in depth with each lesson. And I'm going to do the 5E model because that's how I set up each of my lessons. So lesson 1, as I mentioned before, is looking at satellite data and how to analyze that satellite data. So I first have students reflect, what does that term climate change mean? What have they heard about this term? What do they think about this term? And kind of just put it into a cloud to get familiar with what they already know in order to compare it to what they'll learn later on. From there, I introduced them to a video from PBS NewsHour, where the director of the GISS Center, Dr. Gavin Schmidt, talks about climate change and when the best action to take, which was back in the 70s and 80s, but the second best time is now. So really honing into students that, yes, we've known about this day for a while, and we probably should have done something in the past, but that doesn't mean we can't do anything now. We can still take action now. From there, they get familiar with EOSDIS Worldview, and they're getting instructions on how to pull the data from there. And when they have the data, how to throw it into an organizer and analyze and compare that data to historical imagery from Google Earth. And Barbie, can we go to that video of EOSDIS Worldview? So I wanted to show just how EOSDIS Worldview works, because it is a wonderful site to get satellite data. So you'll come to this first screen where there's an introduction to walk you through if you haven't used this website before. And as you can see from the introduction page, there's a lot of different topics you can go into, such as hurricanes and fires, like the Camp Fire that was so devastating to California. And so you can use this aside from the urban heat island effect. When you go to the main page, on the left-hand side is where you'll actually add the layers of satellite data. So when you click the Add Layers button, it'll first bring you to a hazards and disasters page, so giving you ideas of different topics that they have data on that you can look at. And it's not just data from today, it's historical data from whenever that satellite first went into use. I use the second tab, Science Disciplines, where I can kind of see more categorically what topics there are. Because me, I like to organize by that way. And so my mind always goes to land surface since I'm studying urban heat island effect. And in land surface, you can see it's not just land surface temperatures. You have albedo, you have corrector reflectance, you can look at land cover. But with this particular lesson, we're going to be looking at land surface temperature, which is going to be the satellites Aqua and Terra. And with this, they give you a description on the right of the different satellites. So if you're not quite sure if it's going to provide the data you want, you can read through that description on the right to make sure it lines up with what you're trying to do. And so that's how I checked that indeed I wanted to use Terra in this lesson rather than Aqua or another satellite. And luckily Terra flies over about once a day, so it collects data continuously on a daily basis. And then from here on the left side, you can check different types of temperatures that you want to apply to your map. So I do land surface temperature day because I'm looking at the daytime. And on the screen, you can zoom into different locations, but you can also change the time frame for as long as that satellite has data. So you can change it by day, you can change it by month, or you can change it by year. It will show you data it has available just for the range of the satellite. If it doesn't have data, it'll just show you the regular blue marble image instead. As you can see, sometimes cloud cover can hinder data as well. So you can zoom in up to, I think it's 10 or 5 kilometers. And when you move your mouse over that data, on the left side, you can see it's showing you in Kelvin what the temperature is of that area for land surface. So this is where students are going to be pulling that data and applying it to their graphs, which I'll show on the next slide once this video finishes. You can also make the layering a little bit more see-through. So if you need to figure out where a certain city is, you can do that and find your city that you're looking for. On the top right, there are also some options where you can apply different things. You can have them take a snapshot of the image, which I have them do with this lesson, or if you need more information about this particular resource. And one of my favorite features, you can add a ruler to show distances if you need to do that as well. So if you know like the span of your city, but you're not quite sure how it shows up on the map, you can measure it out. All right, so once the students get that data from EOS Worldview, they'll also go to Google Earth and get historical imagery of that same area to compare the land cover to the land surface temperature. So on the worksheet, this is what it looks like once they put it into the graph. You have the year on the left, the land surface image broken up into 9 parts, and then observations of the land surface. That's going to be very helpful to see if there's any changes year to year with the development of that city. And this example city is Las Vegas, which had a bit of growth in those past couple of years. And then we compare that with the land surface temperature image, and students will calculate the average temperature at land surface, first in Kelvin, since that's what the site provides, but then convert it into Celsius. It's a little of conversion there that they'll need to do, which going from Kelvin to Celsius is not too bad. From there, they'll explain any patterns they saw with the data in terms of the land surface cover, how it's changed over time, in comparison to what the satellites picked up with land surface temperature. They'll then learn how satellites pick up data in a different layering, which you can see in that top right image, how each bandwidth picks up a different thing. And so if they're looking at the images like we just saw, they're looking at the bands that have infrared wavelengths. Whereas you can do different corrections like a combination of blue and red to see different things in that satellite data. So they're learning the inner workings of what these images actually pull from when they fly over to what they actually see when they pull the data from EOS Worldview. And then lastly, they compare the satellites, Landsat 8 and MODIS Terra, to see why we use a variety of satellites in our research and not just focus on one. So what they really get out of that is Landsat 8 has very high quality images, but doesn't fly over that much. If Landsat flies over every 16 days, but MODIS Terra flies there every single day, but the quality and resolution of the images is about 1 kilometer, so not as high resolution as Landsat 8. And then they wrap up with looking at how scientists can use this data and changes in that data to track climate change. So bringing them back to what they did at the beginning and seeing, well, can we model what's going to happen? Lesson 2 starts the ground campaign. So the ground campaign, as I mentioned before, they're going to go outside with thermal cameras. Depending on the available resources, this could be just a simple handheld probe that they point at the ground to collect temperatures. My students will have a FLIR thermal camera that I got from a previous mentor. So there's really a range of instruments you can use depending on availability for your school. They're first going to think about, in the do now, how accurate satellite data is. So thinking, when we see satellite data, do we trust it right from the start, or should we do some groundwork to see, is it accurate? And so there's a demonstration activity that they start with where they have an object about 10 feet away that they measure, but then also 20 feet away, and see, does distance make a difference when collecting that data? So kind of putting into their mind, do we trust it outright? Because you can't trust something outright, you should probably test it first. Then they go into the explore part where they actually go outside with their mobile thermal cameras. And with this, they're using the GLOBE protocol for how to take land surface temperatures. And with the GLOBE protocol, you select an area, grab 9 points of data throughout the area, and make a map, and you have to get not only the land surface temperature, but weather station data of the air temperature, cloud cover, soil moisture. So a lot of that takes into play with grabbing land surface temperature. But there is a link to the GLOBE protocol in the lesson if you need it. And then part 2, they're going to pull that satellite data just like they did in lesson 1 and compare what they got outside versus what the satellites picked up and see, is it about the same or is it vastly different? And so here's an example of data collection. So you're going to take it on 3 consecutive days as long as weather holds up, and grab the average surface temperature from thermal imaging, so the handheld cameras, average surface temperature from the satellites, first in Kelvin, then convert it over to Celsius, and then compare that also with the air temperature from the local weather station. So with that, they compare how much of a difference there is between ground readings and satellite readings, and then they'll come back to layer it and see, was it a large difference or within a good range that we can still accept that data. After that, they compared their results with other groups to see what other groups came up with, since they have different points within that designated area. And then they learn about ground truthing, which is the act of comparing ground data with satellite data to make sure that the satellites are accurately picking up the data. From there, they're going into the Elevate activity, where they actually look into the specs of the instruments they're using. Before scientists do any research, they have to check out the specs of the instruments to make sure it applies to what they're trying to get with the research. So like my team, when we first started out, we really looked into the different FLIR products. We looked into how to tune the instruments and make sure they were working properly and actually the right equipment for what we were doing. And same thing with the satellites. We had to make sure Landsat 8 was the actual satellite we wanted to use, and same with Terra and Aqua. They then look at atmospheric corrections, because the images that we actually get from satellites, there have to be corrections are applied due to atmospheric conditions, like the different gases or clouds that can interfere, and apply those to satellite images that we end up seeing. And then part 3, looking at consistency. So why take data on the exact same day that you'll get it from the satellite and at the same time frame as well? We always want to have consistency with that data, otherwise we're going to get skewed results. And then wrapping up with looking back at the initial question of, do they think satellite data is accurate based on now what they've done out in the field? and looking, did their viewpoint change? You always have to reflect back about how you could change your thoughts as well, not just what you thought from the beginning to end. In lesson 3, we get into that term urban heat island intensity. So first looking at what factors might affect the intensity or high temperatures in the area for land surfaces. So thinking about, oh, is it hotter when I'm at the park versus when I'm walking down the street? From there, they're going to look at an image of change, which is from the NASA Scientific Visualization Studio. And I'll show you in a bit what that looks like. And they're going to observe how the urbanization happens to a city, looking at the land cover and how it changes over time, because that's going to really tie into what they learn about urban heat island intensity. And then once they've done that, they're going to get into the explore activity, where they're going to select a city to observe over a span of time and see how has the cumulative intensity in the urban area changed and where is it more intense in the city as well. So I'm actually going to show you those 2 resources. So Barbie, can we switch over to the video? So this first one is the images of change. And on the bottom, you can pop it open and it'll give you more information about that particular image and what they're showing within both images on the images of change. On the center, it automatically starts with a curtain view. So you can reveal the past image versus the present image. So right now it's showing the past image. And then you can see how drastically it changes to the present image. So urbanization in this case was Shanghai. So my favorite is the curtain view, but you can also do a toggle view. So going back and forth between the 2 images rather than using the curtain. And then there's also the 2-up option where you can have both images up at the same time, side by side, which can also be a very powerful tool as well, especially with urbanization. Now for the explore activity, this is the urban heat island intensity map that was developed through Google Earth Engine by a couple of researchers. And what you do is you select a city of choice. And once you zoom into that city, it'll show you the areas that have higher intensity than other ones. So the redder it is, the more intense the urban heat island effect is, or on average, how hotter it is than the average temperature of the city. And so what we want to focus on here is the summer daytime UHI intensity. So on average, it looks like here in Atlanta, that's going to be about 1.42 degrees Celsius above the average temperature of the city. So you can see there's bluer areas where it's kind of more of those suburban parts of Atlanta. But then right in the downtown area, we can see the redder, more intense parts of the city. So once the students have gathered that data, you can see on the image at the right, they're not only getting the temperature data, but they're also collecting images through Google Earth Engine and Google Earth Explorer to show how it's changed over time so they can visually see it, but then also can see it through the data as well. For me, it's very powerful to have both. Some learners, as we know, are very visual, others are more textual, so it's good to have both. From there, they will look and analyze their data and compare it with other groups to see what do they observe in other cities, and then learn about what that term urban heat island intensity means through 2 sources. One is a video from NASA Goddard on urban heat islands and how they were able to determine that effect was happening. And the second is an article from NASA on vegetation effect on UHI intensity. So starting to look at those mitigation solutions on how they pick high intensity areas within urban areas, implement those green strategies to help start cooling down those areas. And then lastly, they'll create a mind map of all the information they looked at with urban heat island effect, start branching what are the main ideas about urban heat islands, And then branching from there, what are the things that contribute to those main parts of the urban heat island effect? After that, they're going to look at demographics. This is something that can often be overlooked when looking at urban heat island intensity. We don't want to just look at the land surface temperature. We also want to compare it to the demographics of an area, see what populations are being affected and which ones are in those hotspots. As I mentioned before, they often tend to be the more developed areas, but with those populations, we tend to see young children, the elderly, and also the poor as well. So we want to make sure that we're identifying these hotspots and who lives there in order to help them out. And then lastly, we're looking at the main factors that determine urban heat island intensity, so going right back to that so that students can show what they understand about it, but then take it to the next step. What can scientists do to mitigate and reduce the urban heat island intensity? Which ties into lesson 4. So they're starting to learn about mitigation solutions. So what I have them first is think back to what they did at the end of the previous lesson, looking at what are steps to reducing urban heat island effect. And then from there, they're playing one of my favorite games ever developed, the offset game from the Jet Propulsion Lab, where they start to learn about different factors that contribute to the average global temperature rise and how they can start mitigating it, such as changing the types of plants they have, changing how many cars are on the road, start carpooling, building more or protecting forests or planting more trees, changing the solar panels, all those things are within the game. From there, they're going to start looking at bioswales. What they're first going to do is look at New York City, and I have them do New York City for 2 reasons. Well, one, my students are from New York City, so it's right in their backyard. But 2, New York City really has been putting in a lot of bioswales in the city to help deal with the urban heat island effect. So I'm going to have them go to this website that is hosted by ArcGIS, and where they have the data of where bioswales are being planned to put in, which ones are currently under construction, and which ones have already been developed and finished. And so they're going to initially select 3 areas or 3 watersheds and take a picture of those watersheds and see what number of bioswales are already there, which ones are construction, and which ones are finally finished. And see, is there a pattern to where they place these bioswales? So in the second part, the explain, we first look at their findings, but then they learn about the structure of bioswales. So looking at each part of it, because each part has a very specific purpose, not only for reducing the urban heat island effect through reducing temperatures, but also with taking in stormwater runoff, which is a contributor to urban heat island effect as well. And what they'll start to notice with looking at the placement of these bioswales is they're often placed in areas that have a change in elevation, so think like a hill or something, but that also feed directly into a local waterway. Like with the first one, the Gowanus Canal. So they're trying to make sure that the stormwater runoff doesn't overflow those waterways, but also help reduce the surface temperatures that are happening in that area as well. So capturing the water, but then also turn in effect evapotranspiration. And then from there, they're looking at, let me go to the next slide. How do these mitigation strategies help with reducing the urban heat island effect? So going back to that opening question, why it's important to do these strategies, what they learned prior that can help them determine the effectiveness. So looking at doing ground campaigns with thermal cameras to see how effective these mitigation solutions are, but also using satellite data to look at that as well. And then why is it important to have data to identify these trends or patterns? So like how back in the beginning, when I talked about our research, how we identify those hot and cool spots help us to identify why we want to put a mitigation strategy in a certain place. So identifying those patterns. Which brings us to the Capstone Project. So this is where the culmination of everything they've learned and every type of research method they've learned in the previous lessons, they're going to put into use for a specific research project. So I have them first think about how can we use everything we just learned to determine what could happen in the future of a city. From there, they watch a video that's from a series of videos like on a unit about climate change. And this one, once again, is given by director Dr. Gavin Schmidt about comparing climate change to a doctor appointment. So looking at what are those initial symptoms? What type of strategy do you take from there to relieve the symptoms? So it helps them kind of put into mind how when they go to a doctor and they get a diagnosis, it's the same thing that we do in research. We have to first diagnose what's going on and then provide strategies of what to do next in order to reduce whatever is occurring. From there, that is when they're given the time to start developing their project. And so I'm going to go to the next slide to show you the breakdown of the steps. So step one, with a partner or group, they determine their city of study. So they can pick any major city as long as they get approval from the teacher. On the worksheet, I do have a list of about, I think, 20 cities that are suggested to use. But as long as the student can make sure they can get data from other cities that aren't on the list and get approval from you as a teacher, that is completely fine. Once they have selected their city, they then take a look at the historical data from Google Earth and compare that to the satellite data of land surface temperature from EOS Worldview. So it mimics exactly what they started doing in lesson 1, but now they're doing it for a specific city that they are studying. Step 3 is determining urban heat island intensity. So using that website they used in lesson 3 from Google Earth Engine and looking at their city in particular and seeing, well, how has intensity changed over time in comparison to the development of that city? Step 4, they're looking at the demographics of those hotspots. So like I mentioned before, it's not just about looking at the hot and cool spots, but also looking at who's being affected by those hot and cool spots and getting the community involved with it as well. Step 5, predicting the future of the city. So climate models help us to understand what could happen in the future and what steps we could take to either help that future or if it's showing something different, how we can avoid that future. So this is where they have to use that data from the historical past, so the Google Earth imaging, the EOS Worldview satellite data, and the urban heat island intensity to predict what they think will happen. Step 6, they then create a well-developed argument for change. So they have to use the data they collected to support why they're suggesting a change in that city. And then step 7, propose a plan for change to improve the city. So this is where they'll create the infographic poster, which is the final step, and have not only their data on the poster to support their argument, but an overview of what mitigation strategies they suggest for helping to improve that city. Once they have their poster, they have to have other sets of peers review that poster, so the peer review process, to make sure what they have backs up what they're trying to do, but also they have the data to support their findings and what they suggest. I wanted to highlight all the resources I used in this unit, just a quick snapshot of all those, since I tend to use a lot of outside resources because I feel it's really helpful to integrate and show students where they can get information from. So this is just an overview from lessons 1 to the capstone of all those resources I mentioned, such as EOS Worldview, NASA Images of Change, the Offset Game, and Globe, which if you're not familiar with Globe, I highly recommend checking it out because they have great campaigns, not just for land surface temperature, but for clouds and mosquitoes and a lot of other things as well.